Can everybody hear me up there? Are we good? All right. Okay, last time we talked about Savage's theorem. We mentioned that to get rid of non-determinism when you are space bounded in computation, suffice it to only square the space to get a deterministic version of the same computation. Can you guys still hear me up there? Good. That was divide and conquer, kind of recursive simulation, a lot of space reuse, very extreme case of space reuse, but it worked, and we only had to square the space to get rid of non-determinism. For time, we don't know how to do this. So to get rid of non-determinism in time, that's the P is equal to NP question. We don't know how to do that, how to simulate non-determinism efficiently in time. But efficiently in space, we do know it's squared. Now, is squared the best we can do? That still we don't know. Maybe you could do it a little bit less if you're more efficient. We don't know if the square is a lower bound. We know it's an upper bound. That's Savage's theorem, right? And Immermann's theorem, we mentioned that non-deterministic space is closed under complementation. That too was open for a long time, and it's a similar proof strategy to Savage's theorem, a lot of space reuse. And we don't know if that's true for time either. That's the P is equal to co-NP question. And then we gave full theorem proofs of these. For extra credit, we're not going to go through that in class. It's a bit involved. But for extra credit, you can dive deeper into that if you wish. It's all on the website. So that leaves us with the Chmosky hierarchy augmentation, that P space is equal to NP space. That's a corollary of Savage's theorem. That non-deterministic polynomial space is equal to deterministic polynomial space, and that both are equal to the complement of non-deterministic polynomial space. That's Immermann's theorem. So now we can label more regions here on this extended map. And of course, exponential space is equal to co-exponential space. Exponential space is closed under complementation, non-deterministic, and so on. So we keep adding to this diagram as we go and understand more regions, and you'll see how it keeps evolving, right? And we mentioned that the space and time hierarchy theorems stated that there's languages that can be recognized in a certain amount of space, but in no lesser space than that, and same for time. So the space and hierarchy time complexity classes are infinite. You can always recognize more languages or solve more problems if you have more time or if you have more space, or both, right? But that doesn't answer the question of how dense these hierarchies are. Maybe it takes an exponential increase in space to get new languages. Maybe it takes an exponential amount of time extra to get new languages. Now we talk about the denseness. So we keep splitting here. So the denseness of the space hierarchy is very, very tight. Basically, the theorem is that given two space bounds, S1 and S2, these are both asymptotic functions, as long as one is little o of the other, you can recognize certain languages in S2, that's the bigger of the two, that you cannot recognize in space S1. And all they have to do is be asymptotically slightly different than one another. And that small gap, small though it may be, is enough to recognize new and more languages. In fact, an infinite number of new languages, not just even a few or a finite number. So the proof idea, we're not going to go through the whole proof, but it's very similar to the space hierarchy proof to begin with, except this time when we do the simulation, we're very thrifty in space. We try not to waste too much more space. And suffice it to spend only an little bit of extra amount of space to recognize new languages. Diagonalization argument. So even though we're not stating the entire proof right here, if you go back a few slides and look at the space hierarchy theorem proof, we're using diagonalization, and of course dovetailing as well. This proof is a little bit different, but mostly the same as that other proof. A little caveat that the space and time complexity bounds must themselves be computable. So polynomial space, quadratic space, linear space, exponential space, factorial space, all these functions of space bounds and time bounds must themselves be computable, because we already know there's plenty of uncomputable functions. In fact, there's an uncountable number of uncomputable functions, only a countable number of computable ones. But that's just kind of a technical caveat. Most functions that we know and love are computable. It's actually hard to come up with an easy-to-state uncomputable function, even though there's so many of them. Okay, so the space hierarchy is not just infinite. We've already seen that from a previous theorem. Now we see that it's dense. These containment classes are arbitrarily close together to each other, slightly larger, slightly larger. They don't have to take big quantum leaps, like by squaring or exponentiating or anything like that. Okay, so that is a very interesting result. So for example, easy corollaries from that follow immediately, right? For example, logarithmic deterministic space is a proper subset of log square space, right? And linear space is a proper subset of n log n space. In other words, there's languages, for sure, or functions, if you will, that can be computed in n log n space that cannot be computed in linear space. There are functions to be computed in n to the 2.001 space that cannot be computed in just n squared space. So even a tiny little sliver in the exponent of the space complexity bound gives you more languages than, in fact, an infinite number at each and every level. Okay? And of course, any two polynomials, as long as the degree of one is slightly larger than the degree of the other, by however small amount, gets you more space-bounded computations, more functions that you can recognize with the higher space and not with the lower space. Okay? So it's very, very dense as you can imagine, actually, because these gaps can be arbitrarily small. And of course, immediately you see that logarithmic space is not the same as polynomial space. It's an immediate consequence of this denseness theorem of the space hierarchy. Why? Because log is less than a polynomial. In fact, any power of a log, however large, is smaller than any power of a polynomial, however small. So log space is not equal to polynomial space, even though it's contained in it, so it's a proper subset here again. And of course, polynomial space is not the same as exponential space. Again, immediately from this hierarchy theorem, we see that you can do more when you have exponential space than you do when you have polynomial space. Now let's do the same for time. For time, you get another denseness result, but this time, the denseness is not as tight as for space. You have to jump up by a log factor to get new languages, at least a log factor. So if you have two time bounds, T1 and T2, and these are two asymptotic functions, you can recognize languages in time T2 and not in time T1 as long as T1 log T1 is little o of T2. In other words, T2 is greater than T1 by at least a log factor of that T1 function. So again, that's an infinite hierarchy, and it's reasonably dense. You only have to jump up by logs. And each jump, you get an infinite new set of languages you couldn't recognize before with a smaller time bound. But that's the best, smallest jump we can say for time, at least a log factor. For space, it's any asymptotic growth whatsoever, like log log or log log log, or even a tiny sliver of asymptotic growth is enough to get you more space-bounded computations. But for time, you need a log factor. Now, this doesn't mean that a log is the best we can do. It's the best we know how to do. It's the most thrifty way we know of how to diagonalize over T1 bounded functions to get a function that's not T1 bounded. You have to expend at least a log factor. You may be able to do it one day with a smaller function than a log, but we still don't know how to do that. So it's an upper bound on the jump necessary, not a lower bound on the jump necessary. And again, the proof for this, we're not regurgitating it here, but it's 90% similar to the proof of the time hierarchy to begin with, using diagonalization and dovetailing, and you just try to do it more efficiently. Okay? And again, the caveat here is that the time functions and the space functions must be all themselves computable. It's just a technical requirement. It's not a big onerous thing. So the conclusion is that the time hierarchy is not just infinite, it too is dense, but with log jumps, not arbitrarily small jumps. Okay? So immediately there's a result such as linear time is properly contained in time n log squared n. And quadratic time is properly contained in n to the 2.001. In fact, any two polynomials, as long as the degree of one, y, is bigger than the degree of the smaller one, x, d time n to the x is contained properly in d time n to the y. In other words, the smaller polynomial bound time complexity classes are contained in the higher polynomial bound time complexity classes, respectively, for any two polynomials. Okay. And from this immediately follows that log time is not the same as p time, because log is less than polynomial asymptotically by at least a log, in fact, much more than a log. Polynomial is an exponential of the log. Even linear is an exponential of the log. 2 to the log is equal to n, right? So, we also know the corollary that p is not equal to exponential time. They're different. One is a proper subset of the other. That much we know. So these are not open questions like the p is equal to np question. These are immediate simple corollaries of the denseness of a time hierarchy, and conversely, in the previous couple slides, the denseness of the space hierarchy, respectively, for space. Question?
There you have a comparison between d time n and d time n log squared n. Wasn't the requirement a single log?
Yes, the requirement was a single log, and if you had a single log up here, that would still be true. I'm just mixing it up, that's all. I just put a square term just for the halibut, just for the heck of it. But you're right. If it was n log n, that'd still be true. Good. Now you're getting it. Question?
Does the fact that it has to be little mean that if it was, so n log n is n times the logarithmic, but that's equal, it's not strictly upper bounded? So how would that be like?
Oh, I see. Okay, another interesting technical. So he's saying it was little o. So the question is yeah, so n log n is not technically little o of n log n. It's big O of n log n. Okay, so I take that back. You need something bigger than a factor of 1. And then exponent of a 1 here on the log, more than exponent of a 1. You don't necessarily need a 2. I could have made this exponent 1.01. And then that would be enough. Good. Extra credit right there. Submit that to the class website. In fact, you get extra credit for asking the question. If you ask a good question, it's just as important as giving it a good answer, right? Asking good questions, there's a name for the process of asking good questions. Anybody know what that's called? Asking good question. It's called research. Yes, thank you. So good. I'm glad you're thinking this way. You're asking good questions, and good questions make you think and ponder, and I do my best to ask you good questions. And I'm glad you're asking me good questions back. So, very nice. What else? So, a lot of consequences follow from this denseness. So, for example, we know that logarithmic time is contained in logarithmic space. Why? Because you can't use more space than you have time to use, right? And logarithmic space is contained in non-deterministic logarithmic space, because non-determinism is a generalization of determinism. So how many get this 2 first set containments? Okay, let's keep going. Polynomial time is at least as large as non-deterministic logarithmic space, because you can simulate non-deterministic space in exponential time in that space. Right? So to simulate non-deterministic logarithmic space, you can look at all possible combinations that the space can be in terms of all the possible states, all the contents of the tape, logarithmic long. And there's only an exponential number of different states. But the tape now is logarithmic in size. So an exponential of a logarithm is a polynomial. How many get that? So 2 to the log is equal, not just any polynomial, it's linear. So 2 to the log is, 2 to the log of n is just n. And if it was slightly larger than log, it'd still be a polynomial. So that's why this is true. Now, p is equal to np, that is true simply because, again, non-determinism is a generalization of determinism, or put it conversely, determinism is a special case of non-determinism. So that's why this set containment is true right there. Now, why is it non-deterministic time is contained in polynomial space? Well, because in polynomial space you can simulate non-deterministic polynomial time by just expanding out, the tree and reusing space, and you'd nail the whole computation in polynomial time, even if it was non-deterministic in polynomial space. We already know that polynomial space and deterministic polynomial space and non-deterministic polynomial space are the same thing. And so that's why this is true. And by the way, that was because of Savage's theorem, right? The consequence of Savage's theorem. Of course, polynomial space is a subset of exponential time, again, because you can simulate all the states of a polynomial computation in space by cycling through all possible states and tracking everything you can possibly do. An infinite loop will be detected because you know you've been there before and so on. By the Pigeonhole principle, you can should be assured to never cycle. And so in polynomial space, you can do certain computations, and exponential time you can do all the same computations, and possibly more. Right? So that's that's a subset containment there. Now, none of these are necessarily known to be proper, but we just keep going. Exponential time is a non-deterministic exponential time because determinism is a special case of non-determinisms. So exponential time is, in a non-deterministic exponential time is an exponential space, and so on and so on. Okay, so we have all these containments, and we don't know if any one of them is proper. But by the space hierarchy and time hierarchy theorems that we just showed, we know for sure that logarithmic space is not the same as polynomial space because they differ by at least some asymptotic amount. In fact, by a lot more than asymptotic amount. And so by the denseness of the space classes, log space and polynomial space are not the same thing, even though one is contained in one another. Polynomial space is not the same as exponential space, because that's definitely an increase in space, much more than just a sliver, tiny amount asymptotically, but an exponential amount, in fact. So we know that these three inequalities hold. And similarly, by the time hierarchy theorem, we know that these three inequalities hold. Right? Log time is not the same as polynomial time, because that's more than a log factor. Right? Polynomial time is not the same as exponential time. That's more than a log jump, in fact, an exponential time jump. But all these are right in here. So that means this green one is not the same as this green one here. So log time is not the same as p. Right? So one of these three subset containments must be proper by this theorem right here. So when I say this, I mean several theorems. This is not equal to that. That's one theorem. This is not equal to that. That's another theorem, and so on. So this green is not the same as that green, but they're all subset contained in one of the other, in the next one, right? Repeatedly. So somewhere between here and here, one of these three must not have been a one of these three must have been a proper subset containment. How many get that? Okay, good. It's a lot. Now, does it mean that only one of these three is proper? No. At least one of these three is proper. They can't all be equal to each other. So at least one of these three is proper, but two of the three could be proper, or all three could be proper containments. Proper means it's not equal to the set. Right? So A is a proper subset of B if A is a subset of B, but not equal to B. That's what proper means. I don't want to be presumptuous. So that's the definition of proper subset containment. So we think that none of them are proper. Of course, for time, it's the same thing. So between the P and X time, one of this subset containment or this subset containment between NP and P space, or this subset containment between P space and exponential time, one of those three is also proper, and probably all three are again proper. And between polynomial space and exponential space, same thing. One of those three containments must be proper. So that much we know for sure. We've proven that, right? But we think that all of them are not proper. That's a conjecture. And by the way, one of them is P is not equal to NP. But all of them are open, whether they're proper or not. And all of them are just as hard as P is equal to NP, and some of them are even harder than that, because some of them, if they were equal, P will automatically be equal to NP or not equal to NP as a corollary to one of the other conjectures, if that were to be proven. Question?
Very top you say L is a subset of NL, P is a subset of NP. Why is an X space a subset of NX space?
Right here, let's see. X space, why is it? Why, it is a subset of NX space. Yeah, I just didn't write it down. Because I can keep going, right? I mean, this chain never ends, right? If you keep exponentiating things, then you can keep going. So let's do the next few. You know, exponential space, deterministic exponential space, certainly is a subset of non-deterministic exponential space, just like you said. It is, that's true. And non-deterministic exponential space is a subset of double exponential deterministic space. 2 to the 2 to the n deterministic space subsumes non-deterministic exponential space. So now we have a double exponential. And we can keep going and going and going. So this is an infinite chain. It never ends. And all those are open, by the way. I'm just showing you the first 1, 2, 3, 4, 5, 6, 7, 8, the first 9 containments here. But it's an infinite number, and you can just keep piling up. And none of them are known, whether they're proper or not proper. But every 3 or 4 of them, like this, green to green to green, we know at least one of those 3 is not a proper containment. And that phenomena keeps going up the chain, too. So there's a whole bunch of things about the chain that we do know. Certain things must be not proper containments. We just don't know which, specifically. But among every 3, like green to green, that's why I'm color coding it, or this blue to that blue, or this blue to that blue, one of those groups of 3s must be not proper. That much we know for sure. That's proven by the space and time hierarchy theorems. Good point. So among these conjectures, we know that at least 2 must be true for sure. We just don't know which 2, and chances are they're all true. But for sure, they can't all be false. That would contradict the hierarchy denseness theorems for both space and time if they were all false. In other words, it can't be that log time is equal to x space. That's an impossibility. Because in between them, they're sandwiched a bunch of other things that are not equal to each other. So the 2 ends can't be equal. Yeah, question?
Where did that conjecture come from that we they all are proper subsets?
So he's asking a very subtle question, like why am I saying, why are we saying as a species that we think that all of them are true conjectures? Simply because a lot of evidence has piled up in favor of space and time classes that are so vastly different than one another being actually separated, that one contains language that the other one doesn't. Historically, very few times you had equality between 2 classes. When we questioned the equality may have not have been there, the containment may have not have been proper, and we didn't know, and after 10 or 20 and sometimes 30 years, we saw that they're not the same. So there's a lot of evidence, like empirical evidence based on historical developments of what we found out eventually to be true after years or even decades of hard thinking by hundreds of researchers and many PhD theses written about these things and so on. Entire conferences devoted to these classes and their relationships. And so that's why it's an intuition. So in particular, we think that P is not equal to NP. So if you ask any savvy researcher in the field, do they think that one day we'll be able to prove that P is equal to NP all of a sudden, that polynomial time deterministically and non-deterministically are the same thing, that non-determinism doesn't buy you any extra efficiency, or put conversely, that anything you can do in polynomial time non-deterministically, you can efficiently simulate deterministically and track this entire giant bifurcating tree just with a simple linear kind of height-bounded kind of deterministic type computation, that doesn't seem very likely. And another piece of evidence is that for 50, 60 years, we tried very, very hard to come up with efficient deterministic algorithms for a lot of problems in NP and failed, for the NP-complete problems in particular. Traveling salesmen, hacking problems, all sorts of partitioning problems, Steiner tree problems where you want to connect a bunch of points in the plane, allowing new points to be added. All sorts of problems that we need to solve every single day. FedEx needs to solve a traveling salesman problem every single day. How many can see that? I mean, they're delivering packages. If you can do it in less time or less fuel or less manpower, they'll save billions of dollars a year. So will other companies that need to route fiber optic, between cities. If they can solve the Steiner problem efficiently, they'll be saving billions of dollars a year. Intel, when they design chips, they want to minimize the total wire length and the size of the chip, which increases the yield and lowers the cost. They'll be more competitive against AMD and other vendors of chips. If they knew how to solve these problems efficiently, they would too, because it's worth billions of dollars. So there's huge incentives to show that P is equal to NP. Literally trillions of dollars worth of benefit if somebody can nail that down as equal. But they couldn't, and they've been working on it for 50, 60 years. So that's evidence that this conjecture and other conjectures like it are true, that these classes are not the same.
I just find it surprising because you've mentioned before that, like, for example, trying to find a model of computation, we had thought forever that we had that nailed, and then Turing comes along and shifts everything up or gives us a definition that is more precise. It seems like I'm just surprised that we're taking a body of evidence as enough to make a conjecture versus just
Well,
how diverse the field is.
yeah. So a conjecture is just that. It's a conjecture. We may be surprised, but everything points in that direction, right? I mean, we also conjecture that relativity theory is true, and that gravity is inverse squared. We actually don't know that gravity is inverse squared. That's derived empirically. That gravity drops as the square of the distance between the two masses, whether they're stars or point masses or two particles or two galaxies. It could be that gravity drops as the inverse of the distance to the 2.00001, or the distance to the 1.99999. We don't know that it doesn't, actually. So there's actually worse conjectures, more dramatic conjectures than just things like that. But all the evidence point to the fact that it's close to square, close to inverse square. And there's experiments that measure it very, very accurately between two precise masses and, in a vacuum, and they stabilize the temperature and control all the other situations and variables. And there's experiments that point to the fact that if gravity is not inverse square, it's not different than inverse square by no more than 1 part in a million or 1 part in a trillion, or whatever the accuracy of the experiment is. So there's lots of conjectures all over the place, not just in computation. And you mentioned Turing. Turing defined an algorithm. Before that, we didn't define an algorithm, but we also didn't go around thinking that we know exactly what an algorithm is. We just kind of said, if you want to add numbers, here's how you do it. If you want to multiply them, go through this process. Use an abacus or just write it down and do the carry and so on. So we had plenty of algorithms before Turing. We just never thought to sit down and define one in general. It didn't occur to anybody that that's an interesting thing to do or a fruitful thing to do. We all thought and of course, before Einstein, we didn't realize that mass and energy are equivalent and interchangeable. And before Newton, we didn't realize what gravity does exactly. We didn't know about orbits and so on and so on. But occasionally there's a conjecture gets overturned in a dramatic way. That can happen too. So we used to think that primality testing will take exponential time. That to test if a number is prime or not will require dividing by everything from 0 to the number, which is exponential because the number is represented as a log number of bits. So a number in the range at Google only is represented by a few hundred bits. So it's exponential in the representation of the input. Okay? So we used to think that primality testing is exponential time. It turns out it's polynomial time deterministically. That was only proven in 2002, just a little more than a decade ago, a decade and a half ago. That was open for 2,000 years. Right? The Greeks already knew about prime numbers. Siva Varistasthenes is one of the earliest algorithms known, 200, 300 BC. But nobody knew how to compute them efficiently until 2002. And it was proven by some professor and a couple of his undergraduate students, amazingly enough. And the proof wasn't even that long and esoteric. It was just a few pages. So that was surprising. So if we had to conjecture that 20 years ago, most people would have said, it's probably not polynomial time. Now we say the same thing about factoring. We think that factoring a number into its factors, into its prime factors, is not polynomial time. We think that. We're not sure. And a lot of crypto is based on the fact, or on the conjecture, I should say, that that's not true, that you cannot factor efficiently. So if you can't all of a sudden factor efficiently, somebody comes up with an algorithm, a lot of crypto systems will fall apart. A lot of secrets will all of a sudden become plain text because they're based on a presumed hardness of factoring as how the crypto algorithms work in terms of public key cryptography and other crypto systems. And on it goes. So occasionally we are surprised. Okay. Any other questions? It's a good question. Why do we think that? All right, what else? So So we know that P is not equal. So here's a strange result. Somebody proved that polynomial time is not equal to linear space. But what they couldn't settle is which one is contained in which is strange. They just show that they're not the same. So it's hard to imagine even how such a proof will come about to show that two things are not the same, but not show you which one's contained in which. So we know they're not the same, but we don't know which is contained in which. And in fact, it could be that neither is contained in the other. It could be that they're not the same, and each one has stuff that's not in the other. That could be too. We don't know that either, actually. So that's an odd, you can look it up, for extra credit and track this interesting, weird result. And we don't know if non-deterministic linear space is equal to deterministic linear space. But what we do know, I'm just repeating here what I said in a previous slide, at least one of these 7 conjectures, and there's plenty of others down the list, like he was saying up there earlier, at least 2 of these 7 are true. We just don't know which 2. And if you expand the list, is every four of them with 3 containments, at least one of those 4, all the way down the list, at least one of every consecutive 4 of conjectures down this list must be true. You have inequality simply by the space and time hierarchy, the dense space and time hierarchy theorems. That would make it true. So there's a lot of open problems, not a lot of answers of proofs. So I'm bringing to your attention, it's not just a P and P question. It's just one of a very long line of open problems, some of which are much harder than that, because this will be a simple consequence of some of the others. For example, if one day you can show that P is equal to P space, and we don't know that it isn't, then P and NP are sandwiched in between, and they'll become immediately equal to each other as a simple corollary. We don't know that that can't happen. It still may. It's not likely to happen because of what I said earlier. We don't think that that's how it'll be resolved, but we may be surprised. And entire PhD dissertations were written on each and every one of those problems and hundreds of different variations of these problems. There's a lot going on. Okay, so any other questions or thoughts? So, this is where we are in a space-time hierarchy. And the Chmosky hierarchy now, you can look at it through the lens of the denseness theorems of space and time. So we know that P and NP are contained like that, but we don't know if they're equal. But we know that polynomial time and exponential time, so this class here and this class here, are not the same. We know that much because of the space hierarchy and the time hierarchy theorems. We know that polynomial space and exponential space are not the same either. So this class here and this class here are not the same class by the denseness of the space hierarchy. They differ by at least an asymptotic amount. In fact, by much more than an asymptotic amount, by an exponential amount between a polynomial and an exponential. So we know that those two are not the same, exponential space and polynomial space, right? And all the way down the line. We know that many of them are not the same, but others could be the same. And it could be one day that P is equal to P space. We think it isn't, but maybe we'll be surprised. And all these other ones are in between will be sandwiched and crushed in between, all made equal to each other, because they lie in between these two things that one day could come crashing on top of another as equal. But there's plenty of things here that are not the same. For sure, we know that, right? So the dense infinite space and time hierarchies, the complexity classes that we mentioned, now I'm going to put them in here. So inside P, there's an infinite hierarchy of space, infinite hierarchy of time complexity classes. Linear, quadratic, cubic, n to the 4, n to the 5th, n to the 6th. So I'm writing it like this. So this is now not a Venn diagram component of this larger diagram, which is a Venn diagram. I'm writing it like this because if I wanted to write it more correctly as a Venn diagram, all these purple classes will all be encompassing all these other ones in here, and it'll be a big mess. So I'm now slightly deviating from the Venn-ness of this diagram by showing you there's an infinite hierarchy here, and for sure it's infinite. That's not going to collapse because we know linear time is contained properly in quadratic time, and quadratic time is contained properly in cubic time, and so on. And this is all the polynomial classes here. So there's an infinite hierarchy right inside P, and that's a proper hierarchy. In fact, we don't even have to jump by a linear amount, but logarithmic amount suffices, or more than logarithmic amount suffices. Okay. Same thing for all these other classes. There's infinite hierarchies inside each and every one of those classes, and they're all proper. So let me put a few more in, so now you get a bigger appreciation as to what really goes on in this diagram. There's infinite classes all the way up and down within each one of those sets that we've seen and loved all along. So there's a lot more going on here than we've actually even shown yet. And there's a lot more going on here than we're showing even now. But let's take it one step at a time. So there's more infinite space and time hierarchies by the denseness theorems all over the place, and they're all proper. And each one contains an infinite number of languages that the one below it do not contain, and there's an infinite number of classes at each level, right? Each one containing an infinite number of new languages, not containing any one of the lower purple circles contained in it. These are all proper containments. And in addition to that, there's all sorts of other hierarchies that we haven't written down yet. For example, in the recognizable languages, there's hierarchies here of more and more difficult languages to recognize. And the Turing degrees, we already mentioned Turing degrees. Remember that? There's things that are impossible, and things are more impossible than other things. If you had a black box for the first thing that was impossible, the second thing will still remain impossible, even if you could do the first impossible thing for free. So that's more impossible than the other, just like there's bigger and bigger infinities. There's a whole bunch of hierarchies here, infinite hierarchies of impossible things, some are more impossible than others, and those are proper. In the context-free languages, there's hierarchies here too. Within the context-free languages, our languages are called LALR, languages that can be recognized with one token of look ahead, one character of look ahead. And if you can look ahead 2 or 3 or 4 more, you can recognize more and more languages. How many heard of that? Compilers are concerned with that kind of thing. How many tokens of look ahead do you have to do to recognize the full syntax of a language? So there's infinite hierarchies within the context-free languages. There's also infinite hierarchy within the deterministic context-free languages, never mind non-determinism. Even within the regular languages, there's hierarchies. What's the hierarchy within the regular languages? For example, one is called the star height, the clean star, clean closure. So there are languages that are regular, but if you're only allowed one star, not 2 stars or 3, one star to represent certain regular languages, you can only represent certain regular languages with a single use of a star in the regular expression, that you cannot, that if you allow 2 stars, you would be able to denote more languages that you cannot denote with a single star. Okay, so it's the number of applications of a star, and the stars need to be nested. So it's the star height. It's how many nested stars you need, the minimum number of nested stars you need in the minimum regular expression with the least number of stars to represent a certain regular language. The regular language require more and more stars to represent. If you just allow 17 stars, some regular language cannot be represented using a regular expression using only 17 applications of the clean closure in the regular expression representation. So there's an infinite hierarchy right there within the regular languages. And of course, there's infinite hierarchy within the finite languages even, because you can say, make that hierarchy the language size. So languages which only have 1 string in them, put them within one class, and languages which only have 2 strings, 3 strings. So you can even impose hierarchies within these, and I'm denoting them slightly differently because these are not the consequence of the space-time hierarchy denseness theorems. These are like more specialized hierarchies, but there's infinite hierarchies nevertheless all over the place, aside from the purple ones that I'm showing there. So there's a lot going on all over the place. Yeah.
I wanted to circle back to the non-recognizable infinite number of infinite hierarchies. You said that there are some problems that are more impossible than other problems, and I'm a little confused about, doesn't this seem like a binary case? You either can, it's either possible or not possible.
So he's saying, how can one impossible problem be more impossible than another impossible problem? Right? Let me flip that question around. How can one infinite set be bigger than another infinite set? Right? And there's a very precise manner in which that's true. You cannot put a one-to-one correspondence between the 2 sets. So let's talk about infinities for a few seconds. So Cantor said very non-intuitively in the 1800s that some infinities are bigger than other infinities. And what does that mean? It means they're all infinite. And before him, we didn't know what to make of it. All infinite sets were created equal, we thought. But no, he said, and he was right, by diagonalization, some infinite sets are bigger than other infinite sets because there's no way to correspond to one-to-one. And other infinite sets, you can correspond one-to-one, and those are the same size. So they're a very, very precise definition. Now, what does it mean for one problem to be more impossible than another problem? Take the first problem that's less impossible. It's impossible, but let's create a black box for it. Give it to you for free as an oracle. You can query the black box. In one time step, you'll get the answer no matter what. It's an impossible question to answer, but there's a genie in there that gives you the answer for free.
You can do diagonal construction with that.
Yes. You can use diagonalization now to show that even if you had such a genie in a box, it solves one impossible problem, you still can't solve, even using that genie, however many times you want, the other problem. So that makes the other problem more impossible than the first. Because the first problem is solvable with a genie in one step every time. End of story. But the second one is still impossible even given the genie. So it requires a super genie. And guess what? If you get a super genie that solves the second impossible problem, now there's a third one that can be solved using the super genie. And that's more impossible than the second problem. And there's a whole infinite hierarchy of those. Those are the Turing jumps. Right? We talked about that somewhat, right? How many remember that discussion vaguely? All right. Anyway, if you want to dive deeper into that, extra credit, it's on the class website. You know, there's papers on it. There's entire books on it. These are called Turing degrees. Look at the wiki page for Turing degrees. It's one of the links on the reading, not necessarily required, but it's on there for extra credit. Turing degrees. Some problems are more impossible than others. It's a very intriguing concept, right? I mean, it's a very good question that he's asking. How can that even be defined? Well, this is how. You got a free oracle for one, you still can't do the other. That makes the other harder in this sense, even though they're both impossible to do algorithmically. Yeah.
So there's like an infinite degree of impossibilities where like each problem is more impossible than the other.
Yeah.
Would that be the same thing for infinite numbers? Or there's like certain sets that have like even more infinite than uncountable infinite?
Yes, of course. The infinities, there's countable, the infinity of the integers. The infinity of the reals is uncountable. And the infinity of some sets is bigger than the reals. What's a set that's bigger than the reals?
Complex.
The complex set, you can map it onto the reals, actually. Yeah, but it's a very good try. It contains the reals, but it doesn't have more elements than the reals. Just like the integers contain the primes, but the set is not bigger, because you can map the primes into integers. The first prime, the second prime, the third prime. There's a one-to-one correspondence between integers and primes. So pure containment doesn't mean it's bigger. So real numbers. Or, better yet, curves in the plane. Geometric curves in the plane. Drawings, arbitrary drawings in the plane. That's bigger than the reals. That's subsets of the reals, which means it's as big as the power set of the reals. The power set of a set is always bigger than the set. How many have seen that stated before? Where did you see it? The power set of a set is always bigger than the set, even for infinite sets. For finite sets, it's obvious. If a set has n elements in it, the power set has 2 to the n. 2 to the n is bigger than n. But for infinite sets, that's true too. Where have you seen it?
With sigma star and the set of all languages.
Yeah, but the general theorem. The general theorem says the power set of a set is bigger than the set itself. It was actually on the problem sets. If you remember. Started mentioning it. I was hoping somebody would jump and say, oh yeah, I've seen this problem. It's on the problem set somewhere. But how many remember it from the problem set? Just, okay, a few do you do? Okay. I won't question why others don't even remember seeing that anywhere in the problem set, but you know, I hope it's not because you didn't look at some of the problem sets. Okay. And what proof technique it can be used to show that the power set of a set is bigger than the set itself? Diagonalization, our friend diagonalization. We get a lot of mileage out of that at every step, including the space and time hierarchy theorems and everywhere else. Okay, so there's bigger and bigger and bigger sets. They're all infinite, and all these infinities are bigger than all the ones below it. So the power set is enough to get you a bigger infinity. And it's very well defined, instead of all subsets of the smaller set. That's always well defined. Right? Now it turns out that there's infinities bigger than all of those. There's infinities that cannot be reached by repeated power sets. I'll leave it at that for now. If you want to know more about that, which book should you read? That's a meta question. Infinity in the Mind by Rucker. It's on the required reading list, and now you know why, because it answers a lot of cool questions like the one you just asked. What else?
So is there a implicit class for like exponential
Of course, yeah.
And those are not necessarily equal to exponential spaces.
They're bigger. So n factorial grows as n to the n, which is bigger than 2 to the n, asymptotically. So
My question on that is, like, isn't there, like, there's a formula you can use to convert any factorial into an exponential?
there's something called Stirling's approximation formula for the factorial that approximates the factorial as n to the n, roughly. It's actually n to the n over 2 to the n times the square root of 2 pi n, but never mind that. It's roughly n to the n is the dominant term in this expression. So factorial roughly grows as n to the n. It's not hard to show that using some algebra.
So where would we put that on this chart?
So factorial space will be outside exponential space, but still within the decidable. So it'll be right outside this oval here, but not outside the decidable. You'll be right there. Factorial space. Factorial time, then factorial space. And of course, there's bigger functions than that. It's easy to make big functions, right? So he mentioned factorial space, right? So that's n factorial. Right? So that grows very fast. That grows like n to the n. So let's finish it off as a function. F of n is equal to n factorial. What's a bigger function than that? The power set of that. But let's keep it as a function, because this is not technically speaking a set. It's a function of n. Let's not even get so esoteric as busy beaver, because that's not even computable. Give me a computable function that's easy to compute, easy, you know, but it's bigger than that, yeah.
And we add n times.
Yeah, so he's basically saying tetration. But even without that, why don't we take n factorial, which is large, and factorial that, for example. Doesn't that grow even faster? I mean, it's almost unimaginably fast, right? If you factorial the factorial, right? You want one that's growing faster than that? What should you do? Factorial that, right? You want something bigger than that? Take 2 to that power, you know, and you can keep going. It's easy to do. You can do even worse. You can say n factorial, 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 factorial. How many factorials? Factorial times. Imagine how fast that grows. And that's nowhere near the busy beaver function, but it is computable. How would you compute it? Just keep applying the factorial definition over and over again. But very quickly you get more digits than the number of atoms in the universe, even after 2 or 3 factorials, and that'll be it. You can still compute it though. So it's, and where is this class? Factorial, factorial, factorial time? Well, it's outside exponential space, outside factorial space, outside factorial, factorial space, but still within decidable. It's right there. So there's infinite hierarchies. That's where all these are. So I just gave you one example of one of those purple lines here, one of those purple ovals here. How many get that? And there's plenty of others. It's an infinite hierarchy right there. And they're all decidable. Good questions. What else? All right. So let me now mention a few theorems. We're not going to prove these. It's too hard to prove. This was a graduate course. Maybe we'll get into it. But let me just tell you what they state, because they state some unbelievable, cool, hard to imagine facts. But there are facts because these are theorems and we can prove them. So it turns out that there are computable functions that create arbitrary gaps in the space and time hierarchy. So for any computable function g, there exists some other function t such that d time t of n is equal to d time g of t of n. Now, this doesn't contradict the space and time hierarchies. It means that there's a gap between t of n and g of t of n, and g is an arbitrary function you get to choose. So for every g that's computable that you get to choose, I can choose a t that will create an arbitrary large gap between the deterministic time t and the deterministic time g of t. That doesn't contradict the space and hierarchy theorems or the dense space and hierarchy theorems, because this t doesn't have to be computable. If it had to be computable, this wouldn't be true. But if t doesn't have to be computable, you can pick a really esoteric, weirdly defined t that will make this true. Arbitrarily large gaps in time and arbitrarily large gaps in space. And the proof is very similar to what we've seen before. It uses diagonalization, and that those gaps are true in space as well. So in particular, that means there is some function t such that deterministic time 2 to the 2 to the t is equal to deterministic time t for some weird function t. In other words, there's a gap between linear and double exponential for weird enough function t. Now you know why we had this technical caveat on the space and time hierarchy theorems. We said that these space functions s's and these t functions t's, t1 and t2, they have to be computable. I remember that technical, we mentioned it, that technical requirement. And now you know why. Because if they weren't computable, you can get weird pathological behaviors like this, big arbitrary gaps. And it doesn't contradict the space and time hierarchy theorems, which pertain to computable time bounds and computable space bounds, not uncomputable bounds like we allow here. Okay? So that's really weird. And of course, some other corollaries are immediate, that you can have weird enough functions that the time complexity class is equal to the space complexity class. Okay? And it turns out the first gap is between constant space and log-log space. So it turns out that any language that you can recognize on a Turing machine in strictly less than log-log space, you can do it in constant space, which means it's regular. Because regular languages are exactly the languages that you don't need any space whatsoever to compute. You just use your finite control. No tape at all. No extra space. So there's a gap between constant space and log-log space. There's nothing in between. There's no functions that require more than constant space, but strictly less than log-log space. That space is a vacuum. It contains no new languages. So that's interesting. That's not easy to show, by the way. It's an impossibility result. So all classes in space below log-log, they all collapse to constant. It's like a black hole. Any questions about what this result says? Not how to prove it. The proof is difficult. You can look it up for extra credit. It's in much more advanced texts, or research papers. Yeah. Question?
I just want to make sure that my definition is clear. So the gap theorem is talking about there is a function like t of n and then gt of n such that it bridges the gaps, or that there's nothing that it's like vacuous.
You're talking about the denseness theorem of earlier? Or are you talking about this? Okay, so this says that there's a gap in space usage between constant and log-log. In other words, there's nothing that you can do in less than log-log that you can't do in just plain old constant space, which is the same as no space. It means it's regular. It's a finite automata that recognizes it. That's what it says. It's not easy to prove. But I'm just bringing it to your attention because it's a really cool result. It shows you a big gaping gap between constant and log-log. Of course, larger than log-log, it starts, the space and time hierarchy theorems begin to kick in, and there's no gaps beyond, beyond linear for computable bounds. For non-computable bounds, there's still lots of other gaps by the gap theorem we just showed a minute ago. And there's also something called the Speed-Up Theorem, and this is even weirder and more unbelievable than some of these strange theorems that we've already seen. This says, basically, there are languages for which there's no optimal algorithm to solve them, asymptotically even. Another way of saying it, there's functions that to compute them, there's no best algorithm asymptotically. It says that there are problems or languages equivalently that if you can solve it in time t of n, there exists another algorithm that can solve it in time log of t of n, and another algorithm can solve it in time log of t of n, and so on ad infinitum. There's faster and faster asymptotic algorithms to solve or accept the same language, to solve the same function, compute the same function, which is weird. Okay? But again, the trick here that makes it possible is that these languages are very esoteric and hard to describe, and usually you construct them by diagonalization, and this time bound is not necessarily computable in itself. That's the catch. So when you get into non-computable time bounds, non-computable space bounds, you get all sorts of pathological behaviors like this that seem to contradict the space and time hierarchy denseness theorems, except that they don't, because the denseness theorems pertained only to computable bounds in space and time, not uncomputable bounds. I hope this makes sense. I've just stated the results. We haven't proven anything about these. and we won't because it's too esoteric and gets into such deep waters that I'll spare you that. Probably much to your relief, I imagine. Question?
Have we looked into, or has anyone looked into whether these gaps and speedups could apply to non-recognizable languages?
Yes. Yeah, you can get arbitrarily complicated languages, including non-recognizable ones that will, in fact, some of these languages are of that type anyway. They're not even decidable languages necessarily, although there's probably decidable languages that that may satisfy this kind of weirdness. Yeah.
When you say esoteric and stuff, are you talking about languages like the Traveler's Dilemma?
No, that's not esoteric at all, relatively speaking. So the traveling salesman problem, are you talking about traveling salesman? Or like TSP, you mean? When you say traveling sales? Well, if you didn't mean TSP, all problems in NP are decidable, and in fact, they're decidable in exponential time, precisely. You can decide them very simply if you allow brute force enumeration of all possible solutions. So for traveling salesman, if you're looking for permutations or n cities that minimizes tour cost, look at all n factorial different permutations. There's n factorial of them, and I say only n factorial. It's a big number, but you can cycle through all possible permutations and see which one is the cheapest and solve it relatively straightforwardly with a simple enumeration algorithm.
I was talking about the Traveler's Dilemma.
Oh, the Traveler's Dilemma, like the game theoretic thing that's in that paper. So there's a paper on the website called the Traveler's Dilemma, and basically it gives you a game theoretic scenario where the Nash equilibrium is very different than what you'd expect. And rational agents will make very odd decisions that are not optimal and are not rational even, but in practice, they'll get you a better yield, a better return, a better expected win in this game, whether it's economics or some adversarial game. So if you're wondering about that, read that short 5 or 6, 7-page Scientific American article called The Traveler's Dilemma. It's on the website for extra credit. You can read it. But the short answer is no, it's not one of those. Those are perfectly well understood, actually. We know what rational agents would do. They will pick very low values. People will pick very high values, and they'll get better return. Even though from a perfect rational reasoning perspective, that's not the optimal thing to do. To show you another example where the most rational thing to do is not what people do in practice, a Mexican standoff with two people pointing weapons at each other, and they kind of freeze dramatic. Makes a great scene for a movie, action movie. And either one is afraid to put their gun down because the other one will shoot him. The entire world was in a Nash equilibrium like that, except with pistols, it was with nuclear warheads, and we still are, actually. Each side is afraid to disarm because the other side might just attack them, and so both nations, superpowers, nuclear superpowers, maintain their arsenals pointing at each other on a hair trigger just in case. And it turns out that's not unstable, even though it's kind of morally questionable. But in reality, if two people point weapons at each other and they freeze, one of them, even in a movie you see some scenario like that, one of them says, okay, wait a second, let's not do this. I'm putting my gun down, now you do this. Of course, now we're vulnerable, right? That's, from a game theoretic perspective, they just wrecked the Nash equilibrium, and now they're in a very unstable situation. But in a movie, it usually works out. The other person puts the gun down, or else they do a spinning heel kick and not knock their gun out, or whatever, if it's Jean-Claude Van Damme, I don't know. But the point is, you mentioned the Traveler's Dilemma. That's an example of a Nash equilibrium situation where the rational decision is very far away from what people do in practice, and in practice, they fare off better. Usually, if you kind of de-escalate the situation, maybe somebody won't get hurt. Whereas if you do something crazy and brazen, all hell might break loose. Same with nuclear weapons. That's enough for now on that. If you want to know more, read that paper. It's called The Traveler's Dilemma. But short answer, it's not one of these. Okay. Other questions? Okay, so I'm just showing you this kind of pathological things. If you really want to know more about this, in the book by Kozin, which is on the website, chapter 32, the gap theorem and other pathological behaviors, and this covers what I just discussed. It proves the gap theorem, it proves the speed-up theorem, and it's just a few pages. It's 5, 6, 7 pages, but it's pretty dense. If you want to do a deeper dive into that. And then, of course, this abstract complexity theory. If you didn't think this is abstract enough up to now, it gets more abstract. And basically, Bloom in the early 70s did the following. He showed that any complexity measure, not just space and time, but any complexity measure that satisfies a couple of very fundamental, obvious axioms, give you immediately rise to all the complexity classes, their containments, their denseness, the gap theorems, the speed-up theorems, and all the other phenomena that we have. It doesn't have to be space or time. There's nothing magical about space and time. Remember, we talked about other resources when we talked about conserving space and conserving time. We said you can conserve power, right? You can conserve programming effort. You can conserve page faults. You can conserve cache misses. You can conserve bit flips. You can conserve internet messages sent. You know, you can preserve or conserve any kind of resource that you want, not just space and time. And sometimes these other resources are more important than space and time, like power and cost. But he showed that any resource that satisfies these two axioms behaves just like space and time and gives rise immediately to all these other theorems. And these two axioms are very simple. The complexity measure, you can call it phi or some other letter, it doesn't matter. It means that if you have a machine M and an input string W, a Turing machine and a string, the complexity measure of that computation of that machine or algorithm on that string or input is finite if and only if that machine holds. In other words, if the machine keeps computing forever, the consumption of this resource diverges. It's no longer finite. And that's certainly true about space, time, and power, and many other things. Right? If you keep computing, you're consuming more of it, not less. Okay? And the predicate, whether the consumption of that machine and that string, when it computes, of that resource, whether it's space, time, power, or anything else, is equal to a particular number, that's a decidable property. There's nothing undecidable about asking how much space does this use, assuming it holds. How much time did it use before it halted? How much power did it use in watts? You know, how many page faults did it do? How many messages did it send over the internet? These are all obviously computable. There's nothing magical or mysterious about measuring that for a given computation. So as long as you satisfy these two axioms, you get immediately the complexity hierarchy, you get the denseness theorems, you get the gap and the speed-up theorems, and these are all machine independent. And these are just abstract resources. Could be anything else that you want, including space, time, power, page faults, message sent, and a host of other imaginable resources that you consume. So this is even more abstract than before. So it means all these theorems that we've seen all along, we did space and time complexity classes, their containment, proper or not, the Chmosky hierarchy and all that, can be applicable to any other resource that you'd like, assuming it satisfies these two very reasonable axioms. So it's not an artifact of space. It's not an artifact of time. It's an artifact of this, which is even more fundamental. I'm just bringing it to your attention. We're not proving this theorem, but it's true. It's a deep theorem. Again, for extra credit, you can take a deeper dive into it and let me know what you think, what you find out. Yeah.
As a clarifying question, that M-man developing there is a Turing machine and some single given input, right?
Yes.
We're not talking about the languages or whatever.
That's right, yeah. We're not talking about whole languages. We're just saying that machine, when it churns over that input, when it runs with that input given to it, consumes that much of the resource, whatever that may be. Time, space, power, page faults, cache misses, bit flips, whatever it is you're measuring.
So this says nothing about the computability or non-computability of the language that
Yes.
the machine may or may not recognize.
Yes, but it applies to computable, to machines that recognize computable languages, as well as ones that recognize not decidable languages, but recognizable languages. But in particular, it applies to the decidable languages. So all the space and time hierarchy theorems fall from this, and many other resources follow this pattern too. So, he managed to abstract this phenomena, which is, really amazing. Now, there's something that we won't go much into except to define it. This is the tip of a giant iceberg, alternation. So, what is it? In non-deterministic computations, you have only existential states. If there exists a path to success, you're good. Now we're allowing not just existential states, but universal states. Universal state means not only there's got to be some path below you to success, all paths below you must lead to success. So it's a for all, it's not just that there exists. Okay? For all, there exists. This is not a gang sign, by the way. You should be careful. So now with this generalization, you can have some states be existential, some universal, and you can mix them up. And that's called alternation, because you can alternate between existing and for all states, existential and universal states. There exists and for all. And that's a generalization of non-determinism. If non-determinism wasn't enough as a generalization of determinism, this is a generalization of non-determinism. Where non-determinism is a very special case of alternation where there's only one existential state and it's at the root. Here you can have all sorts of existential and universal states, and they can be all over the place. Now, having said all that, there's a whole theory of alternating computations. Computations under the alternation model, just like we had computations under non-determinism, which was richer and more general than computations under determinism. That's the next step up. Now, probably much to your relief, that's all I'll say about this. Okay? That gets even more esoteric than non-determinism. But I'll just quickly show you a few results. Right? You can simulate a k-state alternating finite automata with a 2 to the 2 to the k state deterministic finite automata, and that's a power set construction. It's a double power set construction. I'll just say that. We'll leave it at that. And you can have alternating Turing machines, and alternation doesn't, of course, increase the power of Turing machines because a regular Turing machine can simulate all this alternation business with double exponential increase in time and space, but that's okay. And a whole bunch of other results arise from that, and properties. Again, I'm breezing through this. You can define complexity class just like deterministic time, deterministic space. You can define alternating time and alternating space now. And those are different than deterministic and non-deterministic counterparts. And there's a whole bunch of relationships between them, and existence theorem and non-existence theorem and open problems. And if you've ever seen the movie Snakes on a Plane, that's kind of an existential on a plane, some plane. Now it's snakes on every plane. So that's kind of a joke. But it's a terrible movie, but it's good for a few laughs. And that's the difference. Any general questions about this? This is the tip of a giant iceberg. I'm just showing you, a tiny sliver of it. There's a whole new world out there beyond non-determinism. We'll leave it at that. Fair enough? Good deal? So it won't be on the exam. But for extra credit, you can take a deeper dive into that, and I'll be very impressed and give you lots of recognition and credit for it. You want to go and find out more. And if you look at all this stuff with alternation, you learn to appreciate how tame regular non-determinism is. If you thought it was complicated before, it looked tame to you after this. So that's one advantage of looking into this. Plus, it's really cool. And there's quantified Boolean formulas. We won't say much about that. We'll mention it later when we talk about NP-Completeness and p-space completeness and NP-Completeness theory. But some common games fall into these complexity classes. So let me just say that generalized checkers is exponential time complete, just like traveling salesman is NP-complete. And there's problems which are P-complete. And checkers, generalized, you have to have an n-by-n board. The rules kind of remain the same, the obvious rules. Generalized chess is exponential time complete also. Generalized Go is exponential time complete. Generalized Othello is polynomial space complete, turns out. And you can, if you don't know what these, most of you know what chess is and checkers. Othello, maybe not. Go, you've heard of. So Google AlphaGo just recently, last year, solved pretty well, heuristically, a exponential time complete problem by having their AlphaGo AI engine beat the world champion in the game of Go. Now, it doesn't solve it exactly, it's a heuristic, but good enough to beat the best human on the planet. We didn't think that would happen in our lifetime. The polynomial time hierarchy, don't even get me started on that. We'll skip through that. But I do want to show you something really cool. It's called the complexity zoo. Oh, by the way, there's probabilistic Turing machines that can flip coins. Again, don't worry too much about it unless you want to do a deeper dive. But here's something really cool. The complexity zoo. So we've seen P and NP and P space and X time and all these complexity classes. There's a website. If you Google complexity zoo, you'll see it. All these classes are listed, and hundreds of others that we did not mention that all have names are listed too. And of course, there's an infinity of other classes that don't have names. But even the ones that we use so commonly that they have names are there. Context-free languages right there. Context-sensitive languages, right? You know, we have deterministic context-free languages, logarithmic space languages, deterministic space, deterministic time classes. They're all there in the complexity zoo. Here's NP right there, and here's polynomial hierarchy. P is right there. Non-deterministic logarithmic space. Here's P space. And they're all alphabetized. If you click, these are all live links. If you click on one of those, you get a whole wiki page describing the class, how it's defined, what its properties are, which classes it's a subset of, which classes it's a superset of, what are the known theorems about it, and blah, blah, blah. It's a wealth of information, much more than you can cover in a course or even 20 courses. But here's a bigger picture of the complexity zoo. And this diagram shows you class containments. So each arrow here in this graph is a Venn diagram class containment. If you have an up arrow, the larger class of the node represented in the tip of the arrow subsumes or contains, in set containment terms, the smaller class at the beginning of the arrow. And this was, organized by Scott Aronson, who wrote that paper I had you read at the beginning of class called Who Can Name the Bigger Number? How many remember that? It talks about Beaver functions. Good. And this complexity hierarchy now is, so this basically is the Chmosky hierarchy on steroids. I've shown you this Chmosky hierarchy on one slide, and you thought there was a lot of classes there. Well, get a load of this. Each one of those is an oval in my diagram. Of course, it's not color-coded here, but there's hundreds and hundreds of classes here. And some of them we know and love already, like P and NP and P space and deterministic, context-free, and the regular languages. They're all there. I'll point out to you in a minute exactly where they are. But there's a lot going on, and each up arrow is set containment. So it's too many to represent as a single Venn diagram, so they're represented as a graph instead. But here are some of the classes. So 2 to the sigma star is way up there. It's everything, right? So that's the outer circle in my diagram, right? And there's all the recognizable languages. And there's exponential space here. There's polynomial space, P space, non-deterministic exponential time, and these are all set containments, again, by the arrows. Here's the next section, the midsection of this diagram. Again, just to show you where some of these are. Polynomial space is up here now because we're going down. Here's deterministic polynomial time, non-deterministic linear space. Here's NP right there. Okay, and here's the context-free languages. Here's deterministic logarithmic space. Here are the regular languages, very close to the bottom, because they're so straightforward and simple to recognize. So this is, on steroids, my simpler diagram that you've been seeing all along. And now you have maybe a better appreciation of how much more there is to discuss and know and compare and contrast these languages and thousands of theorems to prove about them, about their containments and non-containments, the properness of containments and improper containments. And there's a lot going on here. And so now you can appreciate how simple my diagram is, simple in quotes, because there's much more complicated things going on out there. So for extra credit, look at the complexities on the web. All these ovals are clickable. They're hot clickable things directing you to wiki pages and have fun time exploring it. But, there's a lot going on. Any other questions or comments? And next time we'll start talking about NP-Completeness from scratch. It's a very deep and interesting subject. A lot going on there too, and there's lots of practical problems that we need to solve every single day like traveling salesmen. And then we'll talk about heuristics to solve them, and it'll be fun. All right? So see you next time.